All right, everybody, this is the last lesson for this unit, Lesson 5, Common Ions. Here we're going to see the Le Chaltier principle come into effect. So thinking back to when we did Le Chaltier in the equilibrium unit, if you add excess of a chemical in an equilibrium, then the chemical equation will shift. So for example, if we added chlorine, it doesn't have to be from a silver chloride source. So perhaps we add some sodium chloride here, and we add this to the solution. The chlorine concentration will increase. If the chlorine concentration increases, then the equilibrium will shift this way to the left, and we will get an increase in silver chloride as a response, as we have to rebalance and consume some of the silver and some of the chlorine to cause a shift. So this also means that a solution that already has some chlorine in it will not be able to dissolve as much. So for example, if we start with a solution that has some chlorine in it, then the silver chloride equilibrium will be limited because we'll have a starting concentration of chlorine. So let's give this a look, this common ion effect, and we're going to do it first with this example. So here we have determine the solubility of silver chloride in pure water. So this is a basic question from the last section, so we'll just really quickly go through. We look at the dissociation, we see that it's a 1-to-1 ratio, so we're going to increase what the dissociation will cause the result in some X amount of silver and chlorine in solution. Place that into our KSP equation here, and we can see that the reaction will proceed. We take our square root of both sides, or we use a solver, whatever we need, and we end up with this result here. This X equals 1.3 times 10 to the negative 5. This is essentially the change, and in this case, the change is how much. This is how much AgCl dissolves. That's what this change is. So once you've figured out the change, this is how much silver chloride has dissolved, or how much silver chloride is aqueous. Any other silver chloride beyond this amount would be in the solid form. Okay, let's look at example 2. So in example 2, suddenly we have added some sodium. So, you know, I've used an ice table just to kind of be in the same vein as what we've done before. So here the silver chloride, you know, in this case we have something that does have a very high solubility. So the silver chloride essentially dissolves, and notice it's not an equilibrium here. It's a one-directional arrow, because we know from our solubility rules that anything with a group 1 metal or most halide compounds are incredibly soluble. So we can think of the original 0.1 molar sodium chloride becoming all dissolved, and so this dissolved version over here tells us that we get 0.1 molar sodium and 0.1 molar chlorine. Not a very exciting one to talk about because it's a 1-to-1 ratio. Of course, there are much more difficult examples of this where we have different ratios that come out. Here's the important part, though, that because sodium chloride has effectively a very, very, very large K, it has a massive K. That's why we're getting all dissociation. That means that when we go to look at a silver chloride, and we go and we say, hey, well, I want to now put some silver chloride in this solution, well, we have to treat the chlorine concentration from the sodium chloride, right? We have to treat this sodium chloride concentration as the initial concentration of chlorine. This changes everything, because now the amount of chlorine has a starting concentration, and if it has a starting concentration, then we know that that the math is going to be very different. Plug this math in, and we can see the equation's getting difficult, right? This is only solvable by quadratic. Solve by quadratic. And so this is where I would use an app. I would use a quadratic solver, or my phone. photomath, something like that. I'm going to show you a little trick though. This is going to be a really small amount. We're talking about things that have low solubilities. So there is a very common technique called the estimation method. And in the estimation method, we think about how our starting concentration is 0.1, and you're going to be adding this little tiny bit of x. So if you use the calculator, look, it's 10 to the negative 9. It's almost nothing. If I wrote this number out, it would, and I added the x in, I would have 0.1000000017. I mean, that's just 0.1. So in some cases where we have a KSP that has a very low number, right, a 10 to the negative 10, so a very small KSP, we can pretend that this value here is 0.10. This is the estimate. And so then this would make the math a lot easier. Now, we use apps in our class that let us cheat, to be frank, and so these apps let us skip this having to estimate part, and that's one of the powers of using an app or a computer to solve these equations, is that you don't have to worry about these sort of estimations or difficult calculations. But now this is actually a very easy to solve algebra problem. Well, I mean, I've had a lot of experience with algebra, so I find it to be a little bit more simple. It's definitely simpler than the previous one, which we had to use the quadratic formula. Here we can take away this 0.1 and simply divide by 0.1, which is going to give us the 1.7 times 10 to the negative 9. And so you see, even though we ignored and we technically estimated, we actually got exactly the same number. So in this case, this was a very good example to estimate with. All right, and as before, this x is the same as this x up here, and that's essentially the concentration of silver. And so we can think of this is the concentration of silver ions in the aqueous, which means that it's the same as the concentration of silver ions in the silver aqueous ions. I'm just going to clean this up a little bit. I've made quite a mess of things, so I'm going to have some pretty messy writing here. So I'm just going to write a little bit neater here. Okay. And so that's what we have. So whatever x is, as long as it's equivalent to the ratio that your salt is going in at, then you can treat x as the new limiting concentration, the new concentration. So this is the concentration of silver chloride in a solution that already has 0.1 molar NaCl. So this is solubility of AgCl in a solution of 0.10 molar NaCl. So that's a common ion effect. Look at that. I mean, this is incredible. 10 to the negative 9, looking at the previous 10 to the negative 5. That's 10 to the negative 4 difference, right? Or that's 10,000 times the difference. 10,000 times less. 10,000 times less silver or silver chloride is dissolving in this solution than in the previous. So you can imagine the impacts this could have in the wild. You know, if you even have slightly alkaline water, or so if your water at home has got a little bit of salt in it, then suddenly you could have things like soap that might not work as well, or you could have you could try to be mixing a something, I don't know what you'd be, adding something else to your water, and the reaction won't happen because or won't happen as effectively. And certainly in the lab, this is a huge important deal, especially if you're depending on the solubility on the pure water for doing one of these sort of precipitation reactions. All right, so here's a lead chloride version. In this lead chloride version, we're going to be mixing in some magnesium chloride. So with the magnesium chloride, again, we have a reaction that is in a single direction. We don't have any arrows. Magnesium and chlorine are very, very soluble when they're together. And so we just have to worry about how much chlorine did we actually produce. And so we get a 1-to-2 ratio. So whatever your molarity of magnesium is, you'll get twice as much molarity in your chloride. This is aqueous. And so that gives us our new starting condition for our chloride. So here up here in the top, you can see a 0.2 molar as our starting solution. And again, we're going to be adding 2x to it in this case because it is a coefficient of 2. So we're going 0.2 plus 2x times x, and there's going to be a square. Boy, this is actually going to be a hassle. I definitely had to go to, I think I used Math Papa or something like that to find this calculation. But again, it is a very small number compared to the value of 0.2. So we could also make an estimation. I'm just going to write that E row down here again. We could put x, and then we could just say that this is 0.2 because, x is, we could say that it's about 0.2 since, I don't know what I'm trying to write here. Let's just say that x is almost 0. X is much, much less than 0.2. So we'll just treat it as 0.2. So here's your estimate. This one was calculated with an app. Calculated with app. And so with the estimate and check method, or just an estimate method right now, we're going to do 10 to the negative 5 equals, and we're just going to go x and 0.2, and we just have to square that. So that's going to give us 0.04, I believe. Should we pull out a calculator? Here, I've got Wolfram Alpha open just in case I needed it. So 0.2 to the power of 2. Yeah, it was 0.4. Okay. And then x, and we still have 1.6 times 10 to the negative 5. Oh, I see what they did here. We divide both sides by 0.04. 0.04 gets rid of this. 16 divided by 4, I know what that is. That's going to be 0.4 times 10, and this is 1, 2. So that's 4 times 10 to the negative 2. So I can do a subtraction there, which means an addition. So a negative 3. I'm just going to clean that up. It's 4 times 10 to the negative 4. Should I use a calculator? Perhaps I should. Okay, let's just take this number here, and we're going to do 1.6 times, you can actually use E on this one, which I like, negative 5 divided by, and we'll just put that all in brackets. And we get 4 times 10 to the negative 4. What did I say? Oh, yeah, there it is. Okay. So we did get 4 times 10 to the negative 4. Hate getting distracted by the math. You know that about me. So this is x. So this is the new concentration. So, oh, it looks like I made a mistake in this previous one. Well, that's not good. Okay, well, perhaps let's just pop this into Wolfram Alpha here. I had done this other one in a different app, and I think that it wasn't a very good app, to be clear. 0.2 plus 2x to the power of 2. Let's see what that counts as. Okay, that gives us an expanded form and complex solutions. Did we not get there? Okay, so give me some answers here. Oh, it does not like this equation because it has a cube in it. Well, that's probably why I have a weird number here. Okay, so in this case, we actually have a situation where we have a cube root, and it doesn't like that. It doesn't like this cube root. This actually looks like we've had some problems, so I'm going to even just get rid of this section here. I'm just going to delete it. You know, sometimes things don't work out. So we did really have to do the estimate. I'm sure if I play around with an app, I could probably struggle through. Possibly Desmos would be an option here. We could be really sneaky, and we could, last time what I did was I went y equals, and then I said x times 0.2 plus 2x to the power of 2, like that. That gives me an equation this way. And then I could say y equals 1.6. And let's see if we can just do a -5. How does that work? Yeah, I think that worked. Let's just try times 10 to the times 10 to the power of -5. Okay, that's better. And then we can just zoom in and find the intersect here. So the intersect there is, it looks like it's a 0.2. Oh, it's real small. This is what we're looking for, and it says, well, that's 4, isn't it? 0.0004. So here, this is our answer. So let's put that in there, Desmos, and we have x equals 0.123397. Well, golly, if we round that to two significant figures, 0.00040, or 4.0 times 10 to the -4. Well, that was a lot of work for nothing. So the estimate and check method does work very well. So essentially all you're doing is you identify in the estimate version for all of these salts, you identify the one term that has an addition, and you're just going to get rid of the addition. This will simplify your equation a lot, and you can, even use an app at this point. As soon as you have this little equation here, you can definitely use an app to solve it there. So it is possible to solve even if it's really crazy, but why bother, right? Okay, so let's try the last one on this page, example 4. We're going to have a lead nitrate. And so lead nitrate is very soluble. We can put aqueous here. It is very soluble. We get 0.1 molar of it. It dissociates into lead and nitrate. It doesn't really matter that there's twice as much nitrate because nitrates are always soluble. And then we have our lead chloride. And so lead chloride is a solid, and it's dissociating into its two ions, the lead aqueous ion and the chlorine aqueous ion. One thing I was thinking about over here, you can see my sort of thought pattern, is that these together is another version of writing lead chloride aqueous. Remember, just go back and look at the way we were writing molecular and ionic equations. This is exactly what we did. We took something that was aqueous and we split it. So this is the same thing. This in turn means that, if you can see my little thought bubble over here, that this equation we've drawn, this big equation here, is lead chloride solid in equilibrium with lead chloride aqueous. So that's all we're really doing. I don't know if that helps you at all. It kind of helps me think or organize my thoughts. All right, so I'm taking the The lead that I'm getting out of this reaction here, this is a reaction, it's a one-directional reaction, not an equilibrium. And that's going to give me this 0.10 molar lead in solution. I don't know how much chlorine I have 0 right now. And then I'm going to be adding X to that, and my chlorine's going to go up by 2X. This is going to give me these values here. And I can use an app. This is what I did over here. I went the app way. This is with an app. And I got 1.6 times 10 to the negative 5. Really small number. That seems weird. Well, you know what? I don't trust anything now. Looks like I've had a lot of little mistakes in here. So let's just do this method. This is 0.1 plus X. Put the bracket, and then another bracket, 2X. Close that bracket squared. You know, this is, oh, and that's the same thing. So let's see what that is. Yeah, that is not right. So actually it should have been this X value. So this was Math Papa, and I don't think I'm liking them. So this is 6.1, and that's times 10 to the negative 1, 2, 3. That's actually quite a bit. So let's also try our estimate method. So I'm gonna just we'll get this thought out of the way. We'll put that over here for now, and we're gonna get in there and fix this. The reason I knew something was up is because I saw that this number was exactly the same as this one. So there was something not quite working. Let's try the estimate method. So under the estimate, we would get rid of this plus, get rid of it. And so I'm going to estimate the concentration of lead as simply that starting concentration, 0.1 molar. And I'm going to estimate the concentration of chlorine as some unknown, but the unknown 2X. And then we're going to put that into our equation. 1.6 times 10 to the negative 5 equals 0.1 times 2X squared. Exactly the same equation we've been using for a while here. This is our KSP, and this is our concentrations of lead and chlorine. Okay, this is a solvable equation. Let's see, what's our favorite now? Maybe let's just do Wolfram alpha here. And so this is the exact same setup here. So I'm going to use 0.1 times X times 2X to the power of 2. See what that looks like. And I get a value here. Maybe this is how I got the problem. As it looks like, here's the solutions. This is the one I want right down here. Well, that number is what I'm looking for on the bottom. So I probably just copied it wrong. 0.00632 is equal to X. So let's compare that to our other value, our actual value, and we can see it's 6.1 and 6.3. Very close, probably not worth worrying about. So here, the value with the estimate, which, the good thing about this estimate is I could have even done this by hand if I had to. All right, so the real conclusion here is that we get about 6 times 10 to the negative 3 moles per liter of lead chloride that dissolve aqueous here. If the solution already has 0.1 molar lead nitrate. And that's that. So these are very tricky, mostly because of math. I think that's the biggest problem. The other trick is figuring out what this initial concentration is. So using the solution, so recognizing that a solution that is 0.1 molar lead nitrate means that we have X amount of common ion. So identifying that common ion is tricky. There are definitely more tricky versions of this. You could make some pretty crazy stuff, right? We could Imagine possibly a universe where we even had what if you mixed a solution of lead nitrate and a solution of lead chloride together? What would be how much more lead chloride could you dissolve? That kind of thing. We're not going to do those, so don't worry about them. Let's do one more question. I'm going to try not to get distracted by math. So let's try this one. Silver iodide has a solubility product of 8.5 times 10 to the negative 17. What is the solubility in moles per liter? Okay. So in pure water, we're simply looking at our AgI dissociation equation, Ag plus iodine minus, and treat it as 0, 0, plus an x, and gives us XX. Okay, KSP is equal to concentration of silver, concentration of iodine, and so then we're going to replace 8.5 times 10 to the negative 17 is equal to x times x. Great. So this is x squared. 8.5 times 10 to the negative 17 is equal to x squared. We need to find the square root of both sides, and we're done. Or use a calculator. Either way, we're done. So let's see what that looks like. Do we want to trust this one? Who is our favorite at this point? I'm not sure who's been giving us the right answers the most, but let's try this one. 8.5, E negative 17. So that's a quick way of getting it to represent the 10 to the negative 17 part. So there it is. That's what we want it to look like. And the answer is 9.2. Well, it looks like 9.2, right? We only have two decimal places, so 9.2 times 10 to the negative 9 molarity is equal to x. So solubility of AgI is 9.2 times 10 to the negative 9 moles per liter in water. Okay. Let's go to the next one. All right, what if we had a little tiny bit, well, a reasonable amount in this case, of iodine? So we're going to assume that HI is fully dissociating into H plus and iodine. We do need to write this out just in case you're dealing with something that's going to be making more than one ion, right? So if it was I2, if there's a little 2 here or something, we would have to worry about that and make sure that the concentration. So 0.101 is still going to be 0.010. And this is going to be our I. Okay, so let's get our same setup. I'm just going to steal it. All right, I'm going to copy that. I'm going to paste that over here. Maybe shrink it down a little bit to fit in. And I'm going to fill in the new detail, which is that we're going to be adding 0.010 molar iodine to start. Thinking back, this is how much we can actually get in the solution. Is that going to be significant? Is that X going to be significant? In this example, it's going to be a number that's even smaller. So in this case, instead of writing out, we could write 0.010 plus X, but this is essentially going to be the same as 0.010 because X here is a number that's super tiny, 10 to the negative 9. It's very, very small. So adding something that's 10 to the negative 9 to 0.010 is simply not going to have much of an effect. That's good because that simplifies our calculation a lot. We can now take our KSP equation, so might as well steal this again because we want to be as precise as we can be. So we're going to put this down here. I even need to steal this number because I keep forgetting it. Copy. So I'm doing all the same stuff, except instead of one of these x's, I'm going to be incorporating 0.010. Okay, so we're simply going to be dividing by 0.010, dividing by 0.010, and in this case, this is the same as 1 times 10 to the negative 2. If you divide exponents, you actually subtract them. So negative 17 minus negative 2 is going to be the same as adding plus 2 to negative 17. So my end result is 8.5 times 10 to the 15, negative 15. Whew, that is a small number, right? That's really tiny. And compare that. Look, we've gone so far. Like that was 10 to the negative 9, already very small amount of solution. But now the amount of silver you can dissolve is essentially negligible. This is one idea, right? This could be an idea. Say you had an experiment that had a silver electrode or something, or you had a silver iodide electrode, and you don't want it to disappear on you. You might add extra iodine, and it would force the reaction backwards, and you would not be able to you would not lose your silver salt. Or if you wanted to get silver out of a solution, you could force it into the solid form simply by adding iodine. Buy some cheap potassium iodide, and you could force the silver to come out of solution because of the low KSP of the silver iodide. So the conclusion here is that 8.5 times 10 to the negative 15 molar silver iodide can be dissolved in 0.010 molar HI. All right, I'm gonna leave it there and let you work on these. Hopefully things go smoothly. There's some other interesting ones. Try this one out. In this one you can see that there's an I2, so whatever this concentration is, it's doubled for the iodine. That's really important. And this one here deals with extra silver, but not anything else. And it would be interesting to know, does this one almost looks like the same number as the question we just did. If you work it out, is it? That's going to be my little hint for you. Perhaps it is. All right. Thanks, everybody. Have a great day. And that's the end of solubility.